We're the Teleoperations Console team working for the Florida Space Institute. We were Group L22, and our sponsor was Mike Conroy. I'm Garrison, and I worked on the front end on the controller page and the related components, and I project managed.
My name is Parker. I worked on the back end, more specifically the server infrastructure, the helping with endpoints and modifying past resources to fit our need.
My name is Danielle, and I worked on the front end for the rover connection page and all its related components.
My name is Ramsa Charles. I worked on the back end, creating documentation and setting up simulation and physical rover development.
I'm Hemant, and I worked on the back end, more specifically the endpoints database.
So the problem that FSI wanted us to solve was they need a comprehensive controller for the re-Razor rovers. And the previous iterations were missing some of the functionality that they wanted. The re-Razor rovers themselves are these small 3D printed multi-purpose rovers that are based on a NASA design. And they're used mainly in lunar simulations at the XLIF lab and other places. The main feature they tasked us with implementing was the ability for one user to hop in and connect to and control multiple rovers at the same time.
Our project goals were to develop a console that establishes the connection with each rover in use, manage which rover is currently being controlled by a user, route rover camera feeds to operators, and ensure that the rovers follow operational commands, with our stretch goals being to create a comprehensive startup guide for new users, make the connection process more straightforward, and to Dockerize parts of the system to make it more user-friendly. Our tech stack on the front end side, we use React Native, Expo, TypeScript, and Figma. And on the back end, we use Fast API and Flask, Gazebo 11, ROS2 Humble, and Postgres.
This is the system design block diagram for our re-Razor Teleoperations console. So we start off with the client application. In our case, is a web app. This communicates to our Python server running Fast API and Unicorn. We have three types of endpoints, the rover management endpoints, instruction endpoints, and telemetry endpoints. These, depending, communicate to the database, and they also communicate to the rover on a delay. What's on the rover is an easy Razor controller server, which is running a ROS2 node and has two publishers, wheel instructions and server instructions. These, when the endpoints communicate to these publishers, they have a set of instructions, which depending on the rover that the user is controlling from the web app, will communicate those instructions to either the Gazebo simulation or the physical hardware.
So this is the web app that we were just talking about. The multi-controller is what we ended up calling it. And as you can see here, it's capable of connecting to up to 3 rovers at the same time. And this specific example is showing 2 simulated rovers. That's the 2 on the right side and 1 real one. You can see the camera feed from what the rover is currently seeing, as well as some information about it, the name and IP address, and also the delay that it's working with. That's one of the things we wanted to simulate in the project. And then users are able to simply connect to and select which one they want to control, drive it around with the controls. On the connection page, this is where they would actually connect up to specific rovers, either using typing in the IP address and the port, or using the discovery feature that we implemented on some of the rovers.
This is just a deeper dive on the backend implementation that I had discussed earlier. So, like I said, it's a Python server that leverages Fast API and Unicorn. Fast API is simply a Python framework for user REST endpoints. So these are like endpoints for our connections, the instructions, managing the rovers. Unicorn is what powers Fast API applications. It's an asynchronous server gateway. And since it's asynchronous, it supports these asynchronous Python apps, which is a great use case for controlling multiple rovers. The backend also has a status monitoring every 15 seconds, also called a health check, and the server transforms commands that were sent from the front end to ROS compatible JSON.
So for the backend team, we also worked on developing a middleware server that would communicate between the console and the rover server. And the idea would be to just have multiple instances of a rover and communicating with the rover ID itself and giving the rover management commands. We also implemented the health check, as Parker mentioned, to ensure if there's any kind of disconnection that would be taken care of in the background. And we also worked on error handling and just the communication delay so we can simulate like a lunar. And here's the ERD for our database. We just had the rover table and telemetry table, and then we communicated and we connected it both with like the rover ID and then the public DBs.
On the rover side, we had controller servers, which handled bringing in requests. Even though we working on these controller servers wasn't originally part of our project scope, we could quickly realize we couldn't ignore it. The rovers we received were crashing and throwing a ton of errors, which made development nearly impossible. This meant we had to dive in and do a lot of bug fixing on the controller server just to get a stable working development environment. One of our top priorities was making sure any changes we made were backwards compatible, so existing functionality wouldn't break for other teams or any future work we did. Along the way, we introduced a discovery service, which allowed users to easily discover rovers on the network using their IP address and improve camera systems significantly, both upgrading them and, as I said before, adding in more bug fixes. One of the first things we had to do on our projects to ensure that everyone was up to date was go through and make a master documentation for setting up and using the controller. As our project comes to an end, we've been updating this document for the developers on future teams to use.
This was one of the demonstrations that we took part in at the XLIF Lab. This is for their sponsors, and they invited us to put our software on the physical teleoperations console, which you can see there in the bottom left picture, and drive around some of the rovers in the regolith bin that they have, which regolith is basically lunar simulated dirt. And you can see our controller running on the computer on the top left there.
Last week, we brought our rovers and controller to UCF STEM Day and exhibited the project to various school groups throughout the day. So in addition to giving the kids a fun opportunity to drive the rovers, we gave them an overview of what the re-raster rovers do, how they work, and how they can get involved with similar types of technology.
Right. Well, I hope you enjoyed our presentation about the teleoperations console. We're really excited about the project, and we were really happy with how it came out.